trying to explain the notion of holonomy. Its consequences. So we have a manifold as usual connected and associated to a connection. We have a holonomy group of that connection, which effectively does not depend on the base point. On the choice of the base point. Very key fact that is, in my opinion, slightly non-trivial is that this is a Lie group. To keep in mind what holonomy is, you have some picture, piecewise smooth curve. I draw them linear, there should not be linear. Any piecewise smooth curve. Here's the base point, here's gamma. It's defined by parallel transport of vectors around this curve. So the holonomy group is in the linear transformation of the tangent space, so it's in GL of the tangent space of the manifold, of course, over the years. And the key thing is, the key fact for this, let's call it star. So the key fact for proving star is that the connected component H holds 0, which is the connected component, which is defined by loops which are homotopically trivial. So loops which you can retract to the point, so loops which you can retract to the point. This is so-called restricted holonomy. It's the connected component at the identity of this thing. The key thing is that if you have, if you have an element here, which yesterday I called parallel transport, say gamma t, which depends on t, here say gamma 1 and gamma 0 is this thing, and in the middle you have gamma t, you have a curve of curves, which are homotopically trivial, excuse me. So if you have a key fact for this is, this defines a curve which I'm going to draw like this. The P gamma T, here's P gamma, which connects to the identity. This is clear. You have a big curve, and you have a curve which retracts this to the identity. This is a picture in the holonomic group of these transformations back to the identity. So any such thing here gives you a curve, in the holonomic group. And there's a basic theorem I call the theorem of the Japanese, because I don't know which Japanese proved this theorem exactly. But theorem. I don't know. So the most precise proof I've seen due to various Japanese peoples, e.g. in Kyoto, is that subgroups of GL with this property are Lie groups. So associated to any connection in any base point is a canonical thing called the holonomic group, and it's you look like you're not satisfied.
No, that's fine.
Yeah.
Always property.
Con has a remark. No.
Just identity is identity curve or what?
The identity in GLN.
Wait, you connect gamma, you connect the parts to the identity
That
GL.
P, so gamma is, so let's go through this again, okay? He's asking a good question here. We start with gamma, which I'm calling gamma 1, okay? If it's in this restricted holonomic, that means that there is a curve of curves, which I've drawn here as a picture. Here's a curve of curves, always smaller, right? Which retracts this thing to a point. Okay. That gives a curve of holonomic elements. In the holonomic group, for each closed curve, we do parallel transportation around this curve, and we get an element of the holonomic. So that gives us a curve of elements in the holonomic group. Okay? And now the theorem of the Japanese. So I know Kurnishi, I know Goto, I know these people. They prove that such a group is really a Lie subgroup of GLN, not necessarily closed.
Then this gamma there should be a P of
What, did I draw something?
which connects gamma to identity.
So for each gamma T, this is gamma 1, or gamma 1 is gamma in that notation.
Yeah.
Yes, for each gamma, we have parallel transport around that curve gamma, which is an element of the holonomic group. Right. As I move gamma to the identity, I move parallel transport to the identity in GLN. Maybe that's what you're talking about.
So I'm saying this should probably be a P of gamma to identity, wasn't a gamma to identity.
As usual, some stupid thing by me confused you. I'm sorry. No, but that's good. That's good. It's clear. P of gamma. As I move gamma to the trivial curve, let's differentiate between identity and trivial curve. As I move gamma to the trivial curve, I move P parallel transport around gamma to the trivial element of GLN. So you can connect every element by a curve. If you can connect every element by a curve to the identity in a subgroup of GL, then that thing's a Lie group. That's an immensely powerful statement, because, I mean, otherwise it's just some group. You understand, virtually every group you know, certainly every group you guys know, is a subgroup of some GL. Somehow. I mean, it's non-trivial to construct groups which are not linear groups. You know, it's non-trivial, right? So they exist and they're important, but the things, well, this thing here is an element of G. Okay, that's very, very nice. It is the Lie group, and it's a very useful thing. And that implies that Lie, I'm going to write it as the Lie of the holonomic group is the Lie algebra. I know Kevin mentioned a little bit about this Lie algebra business in his lectures, but I'm going to repeat all of it right now. Okay, so this is very important. Yes.
It says with subgroups of GL with this property.
Can you speak louder? You know I have a problem.
Which property are you referring to?
Hmm?
Which property are you referring to when you say that subgroups of GL with this property? With a property that they are
What properties are needed for this theorem?
Yes.
That you can, that every point in the group, so we're talking about the restricted holonomy here, every point in the group can be connected by a piecewise smooth curve to the identity. I mean, that's a very strong regularity condition, but, right? But you can see somehow, if you have a piecewise smooth curve, well, let's assume it's smooth, then you have a tangent vector. And as soon as you have a tangent vector, you have a lot. Yeah, so you can begin to believe this theorem by these Japanese. Okay. So this is the Lie algebra. And that's very fundamental. So I'm going to remind you of some background on Lie theory. Reminder of some Lie theory. First of all, let's let G be a Lie group. So you all now know what is a group, and you know what is a Lie group. It's a manifold with smooth operation, which is paracompact. And let's notice that this contains its connected component. This is a connected component of the identity. And the identity and in this case that will be the restricted holonomy in that case. And this is a normal subgroup, so the notation for normal subgroup is that. I hope you have used that notation. This notation somebody like Penkoff used, I hope. So this is normal subgroup. In particular, that means that this thing is a group, and in this case it's accountable, because you only have countably many components, accountable Lie group, if you like, and discrete group. So it's a countable group, and usually it's very small. So usually it's finite. You see, the point is, if you have a non-trivial group, then you have this guy here, the connected component. That says this thing normalizes, G normalizes this. You understand what I mean, normalizes? It says an element of this thing, you conjugate it, it stays in it. It normalizes it. So you have a linear group or any Lie group, you want to know what the possible normalizer is of this thing, right? This possible normalizer by conjugation, you understand what I'm saying? That your conjugation is x goes to gx, g inverse. That conjugates you have an external element of G operating on G0 somehow in some complicated way. If G0 is complicated, this thing's an automorphism, it's a group automorphism. If the G0 is at all complicated, then it doesn't allow non-trivial automorphisms. I mean, if you compute what is the automorphism group of something you like. For example, a good exercise, I don't know whether you learn any group theory in Penguin, but if you take your favorite finite group, so like an icosahedral group or something like this, if I take some alternating group, then compute the automorphism group of this thing, usually it's a trivial thing. Okay, it's usually, you get some maybe small elements like reflections and so on, but usually not much more. So usually this is finite. But in any case, it's always counting. Okay, that's that. And as I joke around with my friends, there's precisely one distinguished element of a group, namely its identity, right? Because, right, it's distinguished by the obvious property, and every other element you get by just multiplying by that element, right? So there's precisely one distinguished element. So this thing, which we write as German G, is the tangent space at the distinguished element in G. Notice, if you have here a curve in the holonomic group that is smooth, that you will get a tangent vector at the identity, and that says that a curve of curves gives you a tangent vector or something in the Lie algebra. This will be interesting. Yeah. So the Lie algebra is just the tangent space for that. That's a manifold. We've talked about the tangent bundle and so on. This is just some stupid thing. Now, I like to write the elements of this thing as letters like that, C. If you have C in this group, in this Lie algebra, then the basic theorem that you have here, that you need to check, and it's completely elementary, is that this defines is tangent, so here's the identity, here it's C, so C is tangent to a distinguished curve. Now, beginning in mathematics, physics, you certainly know by now, because you were good students in K-1's course, that this is sensational because if you have a tangent vector, B, in the tangent space at some distinguished point of a manifold, and here's this point, distinguished point, as here, then there's nothing distinguished that it's tangent to. There is nothing distinguished that it's tangent to. Object draws a curve there and it's tangent to that. Right? You could draw a curve here. Maria wants to ask one of her great questions. Here's Maria's curve. Right? There are many, many curves which are tangent to that vector, that define that vector. A tangent vector is an equivalence class of curves. Right? It says that the first order development of these curves is all the same. It has the same point, image point, the same linear part, but at higher order terms, they may differ. And that's, well, here's an example. So here's Maria and here's Abek, and they're the same from the point of view of tangency. But here, in the Lie group, there is a given a tangent vector, there's a distinguished curve. What is that curve? Well, yeah?
What does it mean, distinguished?
I'm going to say what it means. Well, you can guess. Your English is quite good. So a distinguished, it means among all these curves, it is distinguished.
Unique?
Hmm?
Is it unique? Is it unique?
Among all these curves, it will be distinguished. Now, your English is excellent. Everybody's English here is excellent, but I'm reminding you of the meaning of the English word distinguished. It means among all these curves, I'm going to select one out and tell you it is distinguished, and it's unique by the properties that I'm going to, by a certain property. That's what it means in mathematics, distinguished. Maybe you're thinking of a British fellow is distinguished wearing a suit and tie. You see, that's another meaning of the word distinguished. Maybe you had this in mind, thinking about a British fellow, or a British man, or a British... The Queen is distinguished, reading her manuscript at Christmas time about Brexit. You see? Maybe that's the reason you were confused. You were thinking of the Queen, whom I like, by the way. She's great. Okay. So what is this curve? This curve looks like this. I'm going to draw you a picture of the manifold. Here's the identity. And here's a point in the manifold which I will call G. Well, it's the element of the group, so I'm allowed to call it G. Right. Here's the Lie group G, and here's an element G. Right? Now you have left multiplication by G. You can do it one way or you can do it another. So you have left multiplication or right multiplication by G. Right? Those are multiplication operators on the group, right? Left multiplication means x goes to G times x. And right multiplication means x goes to x times G. Those are two different operations on the group. Right? So for example, we take left multiplication, push forward of C. Okay? I push it with left multiplication, and that if you have C here, you have left multiplication of C here. Left multiplication at G of C. Okay? Right? I mean, it's okay to push things around with the group elements.
Can you do it canonically?
It's completely canonical. What are you worried about? I have a point in the group. I call it G. I have a tangent vector at the identity. I take left multiplication by G. I haven't done anything non-canonical, right? Yeah, and now it's an operator on the group, left multiplication. So it's a diffeomorphism of the group. It pushes forward tangent vectors. Right, that's completely canonical. Okay. So this thing I call C hat at G. And C hat is a vector field on G. Right? Because at every point you have a vector, and it's smooth, because the operation is smooth, everything's smooth, right? So given an element C, I could have done this by right multiplication, and then I get what is called a right invariant vector field or a left invariant vector field, depending on left or right. So in that sense, you're right. It's canonical up to choice of left and right, which is important. Right, because these two operations are different. These two operations define conjugation. Right? So that we get this vector field here. Yeah? And note that if C1 to Cn is a basis of the tangent space at the identity of G, then C1 hat to Cn hat trivializes the tangent bundle. The tangent bundle. It is a global frame. If you take a dimension 2 thing and you push it around, it's independent everywhere. So you get a global frame. This is a global frame. So C1 hat to Cn hat is what we, as you know, global, it's called global frame. By the way, you can see the way I'm talking, and believe me, Cartan was the guy who developed all this theory. And Cartan was the guy who developed Riemannian geometry after Riemann. Okay, so this is very closely connected to Riemannian geometry. It is no accident that the first basic books in this subject, for example, written by Helgesson, are written from the point of view of Riemannian geometry. Yeah.
I still don't understand how do you define the push forward operator?
Well, let phi be a mapping from manifold to manifold. Smooth. So we then have a mapping push forward. Let's say push forward at a point P, pushes forward the tangent space at P to the tangent space at phi of P. What is a tangent vector? Tangent vector is differentiation. Right? So I have to define what phi P of f is for f, a function defined near P. Near phi of P. I have to see near phi of P. Yes, I get a map from here to here. I want to define it. So f means a function, a C infinity function near phi of P. If you like sheaf theory, this is in the sheaf of sections of C infinity function. What is that? Oh, no. I'm sorry. I have to push forward something. Phi of C applied to a function. There's so many things that you have to do. That's the reason you're asking the question. I take a tangent vector here, I push it forward here, and apply it to a function there. Yeah, it's terrible. So what that means is you apply C to phi to f composed with phi. Right? Okay? You pull back the function, differentiate it. What do you want?
Like can you apply, so C is an element in the tangent space, right?
C is an element of the tangent space at P. It differentiates functions at P. If you want, I'll say what I mean by that. You take a local curve, and you apply it, and you differentiate along that curve. Right? Okay. Now, I want to push it forward. That means I have to differentiate functions at phi of P. So I have to say what is the push forward, starting at P, of a tangent space starting at P, applied to a function f. I just compose f of phi. This is a function at P. I differentiate it. This is the push forward. It's called the differential of the mapping phi. In your Mickey Mouse mathematics, you write down d of phi and you write down the Jacobian matrix. Right? So the Jacobian matrix is not a matrix. It is a canonically defined mapping between tangent spaces. That's very, very important. So I'm glad you asked. It's good to review these things. So that was Maria's question. How the heck do you define this thing? And now you admit I've defined this thing, and now you admit I've got a smooth vector field. Okay. Now, anytime you have a smooth vector field, you have a vector field on a group And you should say, if you want to impress your professors in mathematics, this is ODE. Physics people know this, they only know about ODEs, right? A vector field is ordinary differential operators, right? And you should, if you really want to impress somebody, you say, well, this is a local action. Right? By the real numbers. Right? Not necessarily global. It's a local action by the real numbers. That's all this stuff, so the local action of it. Aha, 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 aha. It is global. When is a local action not global? Okay. So you should ask the question that the 6-year-old grandchild asked, when is local not global? Right? Local means it's only defined for a certain time. You can make this precise. I hope you've made it precise sometime. If you have not made this precise, what this means, the domain of definition of a local action. Yeah? You can make that precise. That means the orbit is only defined for a certain time. Now the thing is, this certain time, if this this tangent vector, the identity, is tangent to a local orbit. Yes? A local orbit. That's just ODE. And then I go out here, and maybe it only goes so far. But then I go out here, and I say, well, that's just push forward here. It's defined for the same amount of time. That's push forward. It's defined for the same amount of time, and so on. This action is global. What happens that local actions are not global is the time that they're defined for goes to 0 along an orbit, right? It goes into a, you can't go, yeah. So this is a good question, and here the action is in fact global. Check. Just because the action here is just g times the action there. Okay. So xc gives you xc hat and gives you a one parameter group for the action of xc hat. And then, since you're all good students, you say, okay, my professor told me to ask the most trivial question I can ask. Yeah? Maria always asks these trivial questions, and they're good. I'm not insulting you, don't worry. So, what is the simplest example? Well, what do you mean for G? Well, G equals the real numbers with addition. Well, maybe that's too simple. That's too simple. Let's make it a little bit more complicated. Let's make G equal the positive real numbers with multiplication. It's a little bit nuts, right? It's, as Abek says, it's the same, all right? But I think multiplication, I mean, as easy as, I don't know about you, but when I teach analysis 1, I start with the real numbers with addition. I don't know, the usual thing, you start, The reason you do that is because you have the group structure on the integers, and then you construct all this stuff, and the multiplication is slightly. It's a Lie group, and the tangent space at the identity, which is 1, can be identified with the real numbers by a basis. Element tangent space. So here are the positive real numbers. Here's the point 1, and here's the tangent vector 1 by a basis element of length 1. So let's call this basis element of length 1. Okay. Now we go to this 1 parameter group. Define. I call it C. Defined by C. You got where I am. I take the multiplicative real numbers, I take the tangent space, I take some basis element, which is, right, C, right, defined by C. Now I have this 1 parameter group. I hope all of you who have been assistants and graders and in applied calculus -5 know what the map is, what this 1 parameter group is. This 1 parameter group is defined by T goes to e to the CT. This is the 1 parameter group. The 1 parameter group defined by an element of the tangent space at the multiplicative real numbers is called the exponential function. Isn't it? Yeah. Okay. So, and of course, this exceed, you have different 1 parameter groups depending on what C you use, but not much different because it's only the length, right? Or you can make it minus C if you want. Okay. So the exponential function is the thing you have. So in general, Cartan or whoever it was, you should know in mathematics, Cartan developed almost everything at the beginning. And Hermann Weyl had the sense to read Cartan and to write it down beautifully. So in Hermann Weyl's works, in my mind, there's nothing really new. It's only organization of really well-known things, for example, due to Cartan. So all of these things are due much earlier, certainly this stuff, but in general you should think Cartan, Weyl. And Hermann Weyl had very strong connections to physics, as you know. And so he had the sense of writing these kind of things down so that physicists can understand. It's a very important country. So this is the simplest example. So if G is a Lie group, then we look at some element of the tangent space at the only distinguished point, right here. There's only one distinguished point in here. This defines the curve C hat, a vector field on this thing. And this defines a 1 parameter group which integrates that vector field is called X of CT. That's notation, but it's very, very good notation. Okay? Yeah. So the Lie algebra, which is denoted by this, is an algebra. We're not going to talk about what it is as an algebra. Is really defined by one parameter subgroups. It's incredibly powerful. Now this thing is a Lie algebra. What is the algebra structure? The genius of mathematics, this is my last day, so grant me the chance to make propaganda, is to take very complicated stuff, find what the fundamental things are. But physicists do not do this. This is one of the reasons physicists are geniuses. In order to do physics, you have to be a genius, because you stay at the level of complicated nature. What we do in mathematics, we take all this complicated stuff and we reduce it to algebra. And then you must be powerful in algebra once it's been reduced. I will tell you, once it's been reduced, there are many algebraists who don't give a healthy you-know-what about what the reduction was. They just do here at the level of algebra. Okay, once it's been faithfully reduced. Faithfully in the sense that you lose nothing by this reduction. Okay, so what is the algebra structure? Well, you don't have, you see, we do something complicated. You take C and eta in this tangent space. Then you go over and you get these vector fields, C and eta. Right? And then you go over here and you do the bracket of C and eta. That is a bracket of a vector field. This means really this is the vector field C eta, eta C. I hope you're seeing curvature. Remember what curvature is? It's nabla of x, nabla y minus nabla y, nabla x, yeah, minus commutative. So you should be smelling curvature, and Cartan, of course, was smelling curvature here. Riemann had made some complicated thing, but Cartan saw this immediately. Aha! This is a vector field, and so what you do with this thing is you evaluate it back at the identity. So you take two elements at the identity. This is wonderful. And then you go out the door with these two elements, and outside you have vector fields, and it's horribly complicated maybe. You take a conjugation of these vector fields, and then you restrict back, and you get this. So this thing is a Lie algebra. Well, this is how Lie algebras originally were discovered, right? Right. What does it mean, Lie algebra? It means various things. It's bilinear. It's alternating. Right, I mean, you reverse these things. And the key thing is the Jacobi identity. And you should never write it down the way people write it down. You should write it down the way I tell you to write it down. It says that add Xi, which is defined as this mapping, Xi point. There's a big fancy word used called the adjoint representation of the Lie algebra. It doesn't matter. I'm just defining what this thing is. This is a little bit sophisticated. You see, you put something in here and regard it as an operator. You put something in here and regard it as an operator. Right? Yeah. Guess what are your favorite operators if you're doing calculus? This thing is a derivation. Again, you see connection, right? You see, this is all Cartan. So that is a real. Now I did all of this, first of all, because I talked to Kevin yesterday and he told me he didn't do too much about this stuff, but I want to make sure you understand what is a Lee algebra and stuff. So using this point of view, we have a better understanding of holonomial. Again, this is what Cartan was doing in the early 20th century. Well, I do my favorite picture, my holonomic picture. Recall sectional curvature. What is sectional curvature? Well, we take a tangent space, again our point x0. We take two vectors in here. We take a plane in here, P for a plane, a two-plane. Two-plane. You understand, I don't know, I hope you don't mind my notation. It means a two-dimensional vector subspace of that thing. We call that a two-plane. I hope you understand there are many two-planes, right? The space of all two planes has a name. It's called the Grassmann manifold of two planes. Okay? There's a certain parameter space of all two planes. So for every two-plane, you have, if you take V and W in this two-plane, then you have a picture here, V, and a picture here, W. Right. And you would like to transform that picture to the manifold. There is one way to do that in Riemannian geometry. It is on the blackboard. The way to do that in Riemannian geometry is the exponential map. Is it not true? There is the exponential map from the tangent space to the manifold, at least locally. Each tangent vector is associated to a geodesic, right? And so from this point you have all of these geodesics emanating from the point, forward and backward and so on, right? So you have these things give you curves in the manifold. This thing is called the exponential map. Locally you have this. I want to emphasize that this exponential map and that exponential map are going to be exactly the same. Okay? emphasize that. This will happen this afternoon. I probably will not get to that this one. Oh, I'm sorry, this picture should look like this. Yeah, here's the picture. So you have this picture on this manifold, and since we have a picture into the manifold, you have the exponential map, at least locally, you have a picture like this. You go out here by V, you go a little bit and you go by W, you go backwards by V, and down by W. Is it not true? So in coordinates, two coordinates x, y, you have ddx and ddy, these vector fields. You go out, you have the exponential map, so you can transform all these things out to the manifold. So you go here, we have that vector field ddx on the manifold locally. We have the vector field ddy on the manifold locally. We have the vector field ddx, ddy on the manifold locally. We have the vector field ddx on the manifold locally. Right? Those are vector fields locally that have been given coordinates or given points on the tangent space. Right? You take coordinates and you transform them out. Anybody can do this, but you put them on the manifold with exponential map. Right? These are vector fields. You have a connection. Yes? You can compute this thing. Riemann knew to compute this thing. In fact, this thing has a name. This thing, as you know, I hope, is the Riemann curvature tensor of this thing. That's Gauss curvature, if you like. That's Riemann was a student of Gauss. Gauss, in my mind, didn't understand what Riemann was doing. But Riemann at least understood that Gauss understood what curvature is in dimension 2. And this is a plane in dimension 2, and this is the curvature of that plane. This is the Riemannian curvature tensor evaluated on that plane. Okay. You take a plane, you take coordinates, you take this thing, you take the picture, let's call this Gauss's or Riemann's parallelogram, right? That's how sectional curvature is defined, right? You just take this parallelogram, right? Aha! This defines an element of the holonomic group, right? Parallel transport around here defines an element of the holonomic group. In fact, really what you see it is here is parallel transport, right? Parallel transport, oh, I went the wrong, maybe ddy, parallel transport ddx, parallel transport minus ddy, and so on. Yeah? Well, this isn't quite element of the holonomic group. What is well defined here is you make it smaller and smaller and smaller. This gives you a curve in the holonomic group. And this means that you get a tangent vector in the holonomic group. That means you get an element of the Lie algebra of the holonomic group. Right? I go out, parallel transport around a rectangle. I mean, that's an element of the holonomic. But you make this rectangle smaller and smaller because, right, you're talking about something at a point. So you get a curve in the holonomic. the tangent vector of that curve is precisely curvature. So it says that you want to learn that infinitesimal holonomy that means taking two planes, taking coordinates, taking these rectangles of Riemann, getting this curve in holonomy, taking the tangent vector, infinitesimal holonomy is curvature at the point. At x0 is curvature of, and is, let's say sectional curvature, be careful. But it's the same thing, sectional curvature determines curvature. The sectional curvature of n at x0. Take two plane, take coordinates, follow this thing around the rectangle, get an element of the holonomy, take the whole curve of these things going to 0. That's the tangent vector of that Lie group is wonderful. That says at each point there is a representation of the Lie algebra of the holonomy into the tangent. Right? Now, yes, and this thing, I'm terribly sorry. Into the Lie algebra of the holonomy into curvature of the connection on the tangent space. There it is. I proved nothing here, but this is easy to make precise. Okay. Well, the algebra it means the tangent vector to curves. So you have one parameter groups, subgroups in the holonomy. That gives you in various directions, in various planes, and so on, curvature. And in fact, I've drawn the map the wrong way, have I not? Yes. I've drawn the map in the wrong way. Right, because I needed, you see, my brain is really complicated. I needed the curvature of the two plane to get, yes, I take this two plane, I take this rectangle, yeah. I have this curvature when I at this point, right? And I get a curve by these rectangles, I get a curve in the holonomy group that gives me the tangent vector of the holonomy group that gives me an element of the Lie algebra, right? So that gives me R goes to some element, whatever it is, you see. Okay. This could be trivial. Why not? You asked me some question about parallelizable manifolds or flat manifolds and so on. It could be, by the way, you take a manifold, your Riemannian manifold, you have to be pretty stupid if you can't flatten it out at some place, right? You can just take partition of unity and fool around with it and make it flat. You can make it flat someplace. So that means that, right? That means there's no curvature there. That means that this contribution to holonomy in this contribution is trivial. Right? This contribution is trivial. Right? However, you can only do that locally. Right? You can't do that necessarily globally, right? Maybe, but it'd be a pretty stupid manifold if it was globally flat. Right? However, you ask, and anybody's going to ask this question. Cartan asked this question. Does this generate somehow the holonomial? So Cartan's question, he asked this question in 1915 or 20. It's incredible. Yeah? Cartan's question, does curvature generate holonomial? Well, let's say Lie of holonomial. But that's more or less everything, because if you have the Lie algebra, you have everything. Isn't that a reasonable question? That's the reason I'm telling you I hate homework. It makes me sick to assign homework exercises. It means I'm asking you questions that I know how to solve, and you don't. It's like, Frederick, solve my question. She's 6 years old, here's some trivia question to solve. I hate it. What is mathematics? What is mathematics is being able to ask the right question. Isn't this the obvious right question? Yeah? Isn't this the obvious right question? Does curvature generate? You're trying to understand what the hell is holonomial. You see this little thing I've been talking about. Does curvature generate holonomial? Well, I just pointed out, I'm very much afraid of this question because I just pointed out, we were talking about object just now, and pointed out you can flatten the manifold. You got no curvature there, so you've got no holonomial. Right? You can't do this everywhere. Right? You can only do it there, and so on. Right? Does curvature generate holonomial? And the answer is yes. The answer is yes. And if you consider all points x0 in it, okay. So, let's go through it again. I'm trying to explain something that's deep to you, not some Mickey Mouse mathematics. Given a point in the manifold, in a manifold with connection, you have something called holonomial. Right. Riemann understood this because Riemann introduced homotopy, but Riemann says you should carry vectors with your homotopy and having finer structure. This is then formalized by people like Levi-Civita and so on. You have parallel transport around curves, and you come back and you get an operation on that tangent space, a linear operation, which is called holonomial. Cartan saw this and said, he introduced this. And then Cartan wrote down, this is the Lie group. But it was first proved by the Japanese 50 years later. But Cartan was a genius. This is the Lie group. Okay? This has a Lie algebra. The Lie algebra is determined by all one-parameter groups. It basically determines the whole thing. So we look at what is the meaning of this Lie algebra? Well, it means tangent vectors to curves. Right? What is a curve in holonomial? It's a curve of curves. Right? Because you have, yeah. Well, you shouldn't think about general curvature, you should think about curvature determined by a plane. Curvature determined by a plane, you can go out to x, go up to y, go back to x, come back to y. I remember Stokes and so on, all this stuff here, then you get a curve of the stuff. Yes, that's curvature. But it's also holonomic. And it states that in fact there's a map from curvature to holonomic. Not to holonomic, because you get a curve, what you get is a tangent vector to holonomic. You get a map from curvature to the Lie algebra of holonomic. Yes. You ask the question, does curvature determine holonomic? It would be very interesting, right? Somehow curvature and holonomic should be the same thing. Yes, same thing. You look at it, it looks good. But we were just discussing, you flatten out the manifold and don't do it, touch it. I mean, it's ridiculous, right? So what you're talking about here is at a point you can do anything, but globally you're asking a global question. The answer is yes, and this is a theorem of Ambrose Singer in the 1950s. For you, since you were young, that's a long time ago. For me, I was in high school at that time. I mean, gymnasium. Yeah. For me, that's not very long ago. That's 50 years after Cartan introduced this. The answer is yes. At each point, we have this evaluation of curvature into this holonomic evaluation at each point. Right? And the statement of Ambrose Singer is this entire evaluation determines the entire holonomic algebra. At one point you might not get anything, right? Because you have no curvature. But the manifold somehow is an intrinsic discussion of the Riemannian manifold. It is a beautiful theorem. And you can imagine why it's really true. Because if you say you get nothing at this point, here's x0, you get nothing. And you say, oh shit, I didn't get anything. So I go over here to x1, right, where I know I have curvature, it's interesting. I do my little picture at x1. I get a lot of stuff here at x1 in the holonomic. Well, then I bring it back here. Right? Right? You see what I'm saying? You have to pick up, if you have holonomic, you pick it up from curvature somewhere. If you have holonomic, you pick it up from curvature somewhere. Okay? That is the theorem of Ambrose Singer. That's an incredibly beautiful, deep theorem. Okay? It shows the incredible power of Lie theory also. It says that Lie theory, given the manifold, you have this Lie theory, the entire curvature is contained in holonomic. Right. The entire metric is contained. I said, if you have a connection, you have a metric. At least it is torsion-free and so on. You have some condition. So you have this connection, you have this curvature, all this stuff. Everything is contained in holonomic. Okay? Now, really, everything is contained in holonomic with each evaluation of the Lie algebra of holomorphic, depending on the point. Right? In some fancy language, you have a holonomic sheaf. You have a sheaf, somehow you have, yeah, and yes. So this is the meaning of holonomic. Okay. Now, let me see, I finished almost exactly. Let me just say that in the remaining 2 lectures, I will look at the classification of Riemannian manifolds from the point of view of holonomic. And if I mentioned before, there is special holonomic and there's non-special holonomic. Special holonomic was classified by Berger, by the way, with mistakes. And in the Berger classification, there are more in the Berger classification than Berger claimed. This was ironed out by a great American mathematician, a guy I know quite well, named Bryant, who's at Duke. So if you're interested in anything like this subject, go to Duke. It's a good place. And Bryant is a very interesting man. He's younger than I am, but I think he's still actually Griffiths and such people do. They're very interesting. There is this classification of special holonomic, And then there's everything else. Alright? And everything else is a symmetric space. Alright? And this afternoon in 2 lectures I will explain to you the basics of symmetric space.